Okay, let's talk about scalar multiplication of vectors. The basic idea is pretty simple. A scalar is just a number, a real number. And a vector is a vector. And scalar multiplication means multiplying a real number times a vector. So, definition, if R is a real number, and if we have a vector v, let's give it to ourselves in coordinates, then the scalar multiplication R times our vector, AB, is just defined as follows. You just multiply each of the components by R. It is as simple as that. RA, comma, RB. That's our new vector. Okay? So this is the rule for multiplication of vectors by a scalar. Let's go ahead and see it in action, and then we'll make a little conclusion at the end about what effect this is really happening. What does it mean when you multiply a vector by a scalar? Okay. So let's go ahead and take a look. Here we have part A. We're going to multiply and then graph the vectors. So in part A, I'm going to go ahead and graph the original vector. That is to say, the vector negative 2, 1. And then we're going to go ahead and multiply it by 4 and see what happens. So the original vector is negative 2, 1. That's the end point of it. And so that vector is here. That's our vector negative 2, 1. And when we multiply, so this is part A, 4 times negative 2, 1. Well, what is that equal to? It's equal to, we just multiply each of the components. So it's going to be negative 2 times 4 is negative 8, and 1 times 4 is 4. So that's the resulting vector is the vector with components minus 8 and 4. Let's go ahead and graph that on here. I guess in order to do it properly, I did not plan ahead. We're going to move this down just a little bit. Here we go. In this case, we want to go negative 8 on the x-axis. And so let's just move this a little bit farther so we line up with our dots. Since we have them, we may as well use them. Great. And if we start at the origin and we go down to negative 8, 1, 2, 3, 4, 5, 6, 7, 8, and then up 1, 2, 3, 4, it's going to get us to here. So let's go ahead and draw that guy. There, this is negative 8, 4. Now, things to notice. What I want to do now is I'm interested in comparing the vector before we multiplied it by a scalar with the result of multiplying it by a scalar. And you'll notice that the original vector had an angle, theta, and the new vector has exactly the same angle, theta. The original vector had a length. We could do some calculation and find that length, but I think it's just as easy to tell that if you look at this length and you think, how much bigger is this one? Well, that length and that length again and that length again and that length again, this one is about 4 times the length of this one. So, things to notice, same angle. And it is 4 times longer, or 4 times the magnitude. All right. That's part A. We have multiplied and graphed the vector. Let's go ahead and look at part B, negative 3 times minus 6 minus 2. I might use my same coordinate plane for this one, but I'll just use different colors. So let's see. This one is the original part B. The original is negative 6, negative 2. And that one, we'll put it in green. We go down minus 1, 2, 3, 4, 5, 6, and then down 1, 2 here. So this vector looks something like this. This is our vector, minus 6, minus 2. And then the question is, what happens when we multiply it by negative 3? So first, let's go ahead and carry out the calculation here. Negative 3 times negative 6, negative 2 is, let's see, positive 18 and positive 6. So this is the vector 18, comma 6. Where is that located? Well, since the x and the y are both positive, this is going to be in the first quadrant somewhere. And we're going to need to start here and go over 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and then up 1, 2, 3, 4, 5, 6. It's that spot right there. So let's go ahead, draw it in. Now, what do you notice? First of all, in terms of angle, this one seems to be exactly 180 degrees around the circle from the original. So if this is our new angle, our original angle was all the way over here. So it seems to have reversed the angle, or rather added 180 or subtracted 180 from the angle when we multiplied this guy by a scalar. And why did it do that? Well, the reason is that there's a negative there. When you multiply by a scalar, it goes the opposite direction. And the 3 means that this guy is 3 times longer than this one. If you look at the distance here and think about it, that's about 1 of those, 2 of those, 3 of those. If you were to do that carefully with a ruler, you would see that it's exactly 3 times, and the effect of multiplying by a negative means it goes in the opposite direction. So let's make a note of it. This is opposite direction. And it's 3 times longer. 3 times the magnitude. And in general, this is true of scalar multiplication of vectors. If you multiply by a positive number, it keeps the angle the same, and it simply adjusts the length by multiplying the length or the magnitude by whatever that number is. If you multiply by a negative, well, it does the same thing, but then instead of keeping the direction the same, it switches it to the opposite direction and multiplies the length by the 3 there. All right, that's it for scalar multiplication.